Hello grade 12s, my name is Natasha Barton and I would like to welcome you to this video in which we will be working through question number 8 of the November 2021 Physical Science Paper 1 exam. This question deals with electric circuits. Now grade 12s, I know that there are many learners out there that do not like electric circuits very much or even at all. And I know this because I was one of those learners. When I was in grade 10, I got everything wrong and I had no clue what I was doing. When I got to grade 11, I still did not know what I was doing, but for some reason I started to get some of the answers correct, which is horrible because I did not know how to do it again. So I always panicked when it came to questions on electric circuits. However, because I continued to practice, I made progress, and in the end, I became very good at electric circuits. So at this point, I would like to really encourage you to keep practicing. If you are struggling a lot with the grade 12 electric circuits or section on electric circuits, consider going back to grade 11 and revising that content. If you're still struggling, if you find the grade 11 content to be difficult, then maybe take a step back to grade 10. It's not too late yet. We are not yet at the final exams. So please go and make the effort because it is going to pay off. Yes, practice does not make perfect, but it does definitely make progress. So now that we are done having our heart-to-heart, let's take a look at the formula sheet. We see over here Ohm's law, which relates the potential difference to the current flowing through a resistor. Then we have this new formula that you learn about, that is the Afrikaans version, this one at the top, that you learn about for the first time in grade 12. This formula says the EMF of the battery is equal to the total current multiplied by the external resistance, or we may refer to it as the load, plus the internal resistance. This is the resistance offered by the battery itself. We then have the formulae that you learned about in grade 10 that we use to calculate the total resistance for resistors connected in series and those connected in parallel. There's this formula over here, which is actually the definition for current. It is the rate at which the charge is going to flow. On the left-hand side, we have a whole lot of formulae that we can use to calculate the energy transferred, or you could even say the work done. And on the right-hand side, we also have a whole lot of formulae that we can use to calculate power. This is your formula sheet, and as always, it is very good that you familiarize yourself with this formula sheet. Let's now go on to question number 8, which says the battery in the circuit shown below has an EMF of 12 volts and an unknown internal resistance R. The resistance of the connecting wires and the ammeter is negligible. Now we analyze the circuit. At the moment, the switch is open, right? So here we have an electric circuit that looks rather complex. So I do suggest that you redraw it in a way that makes more sense to you. I'm going to show you how we can do so in a moment. But let's read the first two questions. They say switch S is open. Write down the reading on V1 and the reading on V2. V1 is connected across the battery, while V2 is connected across one of the 6 ohm resistors. Normally, when we have an open switch and we are required to measure or to give readings on voltmeters, then the first thing that should come to mind is the EMF. And I'm going to, for now, define EMF in terms of what you learned in grade 10. We said that the EMF is the potential difference measured across the terminals of the battery when no current is flowing through the circuit. So when we look at the circuit, we see that V1 is connected across the ends of the battery. Therefore, since it is connected across the end of the battery, we know that the reading on V1 is going to equal to the EMF of the battery, which is 12 volts. Now, if we look at V2, we see that it is connected across the 6 ohm resistor. So you may start off by thinking that the reading on here is 0, but I would just like to confirm that with you. If we look at the one side of the voltmeter, we can trace it all the way back to this terminal of the battery, that is the negative terminal of the battery. But if we go to the other end of the voltmeter and go all the way back, we see that we get to the switch. Therefore, this voltmeter is not reading the EMF, and we know that the reading on V2 is going to equal to 0 volts. There is no difference in the energy of an electron here versus an electron there when we are looking at the potential difference that this voltmeter is reading, and therefore the reading is 0. Question 8.2 starts off with the new information. They say switch S is now closed. So if we go up to the diagram, then we know over here where switch S is, we're going to close it. Then they say the reading on the ammeter is 1,2 amperes. The ammeter is over there, so immediately we go and write down 1,2 amperes. And the power dissipated in resistor X is 5,76 watts. Fortunately, they have included that on the sketch. Now they say define the term power. We define power as the rate at which work is done or energy is expended or transferred. For this statement, you're going to obtain 2 marks. Now, before we go on to the next question, I would like us to go back to my suggestion right at the beginning where I mentioned that this sketch, this diagram given to us is pretty complicated and is a bit difficult to understand. So how about we go and redraw it? Once the switch is closed, we know that our current or the current is able to move through the circuit. Current in this section on electric circuits always goes from the positive end of the battery to the negative end. So this is conventional current. Let's try and see how the current is going to flow through this circuit. So exiting the battery, we know that we have the maximum current that will be provided to the circuit. That current is going to flow through ammeter A. When we get to this point, we see that we reach a split. Some of the current is then going to go this way, while the rest of it is going to go down this path. Alright? So at this point, current needs to divide. We see that this current will move through the 6 ohm resistor and come back to this point where it joins the main circuit. On the other side, however, the current moves through the 6 ohm resistor. It will not flow through the voltmeter. Remember, voltmeters have incredibly high resistances, so no current flows through them. Then it's going to pass through the 6 ohm resistor. The same current is going to flow through the 2,4 ohm resistor and join again at this point. Alright, so at this point, what we see is this resistor is connected in parallel to these 2 resistors. These 2 resistors, the 2 ohm and the 6 ohm resistor, are connected in series with each other. We say they are connected in series because they have the same current flowing through them. But the current divides at this point, and that is why the 6 ohm resistor is in parallel with that connection. Now what is going to happen is the current comes back together and is going to return to the negative terminal of the battery like that. That is basically how the current is going to flow. And on that note, we can redraw the diagram so that it looks like this. Of course, we need to close the switch, and we can go and say that the ammeter has a reading of, they gave it to us as 1,2 amperes. This diagram has exactly the same meaning as the one that was provided to us. If you understand this one, then please, you do not need to go and draw a new sketch. But if you are finding this diagram, this circuit diagram complex, then go and practice how to create or how to draw new electric circuit diagrams that are going to aid your understanding. Again, over here we can see, so just to emphasize to you, the current is going to leave the negative end of the battery. The positive end of the battery. This is conventional current. It will flow through the switch. It will flow through the ammeter and get to this point. At this point, the current is going to divide. Some of it is going to go that way through the 6 ohm resistor, and the rest of it is going to go through the 6 ohm and 2,4 ohm resistor. Then they're going to join again. The current will join up again at this point and flow as the total current through this resistor back to the negative terminal of the battery, since we are dealing with conventional current. We now move on to question 8.3, which says we need to calculate the resistance of resistor X. Resistor X is the resistor whose power we know. So we know that this is the value of power. As illustrated just now, since resistor X is part of the main circuit, or rather is connected in series with the battery, meaning that the total current is going to flow through it, we know that the current flowing through resistor X is going to equal to 1,2 amperes. So we know the power and we know the current. We are looking for resistance. If we go to the formula sheet, we see that there is actually a formula that relates the power to the current and the resistance. We say P equals I squared multiplied by R. We know the power, it is 5,76. The current is 1,2. We're going to square it and we write down R. When we manipulate this formula, we find that R, which is the resistance, is equal to 4 ohms. Now, of course, there are other methods that you can use to come to exactly the same conclusion. You can use two formulae, but this is the simplest way possible. So over here, we're going to get 1 mark for the formula, 1 mark for the correct substitution, and 1 mark for the final answer. When we get this answer, we go back to our sketch and we immediately go and write down that the resistance of resistor X is going to equal to 4 ohms. Because if we have it written down on our diagram, we know it's new information that we can make use of in the questions that follow. Question number 8.4 says, calculate the total external resistance of the circuit. Remember, external resistance is given the symbol R. This includes all of the resistors except the internal resistance of the battery. So in this circuit, we have these two resistors that are connected in series. We're going to start off by adding them together. So remember, your resistors in series are added together just as a sum. And this is going to equal to 6 plus 2,4, which gives us a total of 8,4 ohms. These two resistors are connected to this resistor in parallel. So we say 1 over Rp is equal to 1 over R1 plus 1 over R2. In this case, resistor 1 is going to be this connection over here. We're going to call that resistor 1. So we say 1 over 8,4 plus resistor 2 is going to be this resistor, the 6 ohm resistor. So we say plus 1 over 6. All of this is equal to 1 over Rp. We plug this into our calculators as it is, and then we find the reciprocal, and we find that Rp is going to be equal to 3,5 ohms. So this entire part of the circuit has a total resistance, or rather an effective resistance, that is equal to 3,5 ohms. Now this entire part of the circuit is connected in series with resistor X, whose resistance is 4 ohms. So in the end, the total resistance, RT, is going to equal to the 3,5 plus the 4 ohms of resistor X, and that gives us a final answer of 7,5 ohms. RT is actually not the total resistance for the entire circuit, but we can remove that T, and this is the external resistance of the circuit. The marks are awarded as follows. You're going to get 1 mark for your substitution into the formula to calculate the total or effective resistance in parallel. 1 mark for adding together the 3,5 and 4 ohms, and 1 mark for your final answer of 7,5 ohms. Question number 8.5 says that we need to calculate the reading on V2. V2 is this voltmeter that is connected across the 6 ohm resistor in series with the 2,4 ohm resistor. I'd like to remind you that together these resistors have a total resistance of 8,4 ohms. The entire parallel connection, which is this one over here, has a total resistance that is given as 3,5 ohms, and the total resistance we just calculated to be 7,5 ohms. We know that in total, this part of the circuit, the parallel connection, this entire thing, is going to have in total flowing through it the total current. So how about we use the total current with the effective resistance of the parallel connection to determine what the potential difference is going to be across this parallel connection. So we now say, in order to do so, we can say Vp is equal to I times R. This is going to equal to the total current, which is 1,2, and just to help the marker, I'm going to include subscripts. So it's the total current multiplied by Rp. That is going to be, we have 1,2 as the current. Rp we calculated to be 3,5. When we plug this into our calculators, we find that the potential difference across this parallel connection is 4,2 volts. So what is now going to happen is over these two, so we know that in parallel, the potential difference is constant. So across this resistor, we have a potential difference reading of 4,2 volts. And across the combination of these two, we're going to have a potential difference of 4,2 volts. We would like to know what the potential difference reading is only across this part, the 6 ohm resistor. So how about we use this answer in order to find out what the current is that flows through this connection, because if we know the current and we know the resistance of the resistor, then we can find the reading on V2. So now we say the current that is going to be flowing through the 6 ohm resistor, and again we try to include labels or subscripts as far as possible, is going to equal to, we have the potential difference of Vp divided by the R, which is in series, so it's this reading over here. Okay, we plug those values in. We have 8,4, which is the total resistance of that part of the circuit, divided by, sorry Gr12s, I made a mistake, Rp is what we just calculated, 4,2. Rs is 8,4. We plug this into our calculators and we get an answer of 0,5 amperes. So the current that is flowing through the 6 ohm resistor is 0,5 amperes. Now we know the current through the 6 ohm resistor, and we also know its resistance. If we know resistance and we know current, then we can calculate V2. We say that V2 is going to equal to I, the I is that through the 6 ohm resistor, multiplied by the resistance of the 6 ohm resistor. The answer or the substitution is 0,5 multiplied by 6. In the end, the final answer that we obtain is 3 volts. Alright, so for this calculation, you're going to be awarded 1 mark over here for your substitution. You're going to get 1 mark here for your substitution as well. 1 mark for the formula, 1 mark for substituting, and 1 mark for your final answer. That is your 5 marks for this problem. Now, grade 12s, if you have a look at the marking guidelines, which I know in previous videos I have been referring to as the exam guidelines, that is a mistake. If at any point in the previous videos I referred to other methods, see the exam guidelines, I meant the marking guidelines. That is basically the memo that comes with the exam, alright? So if you go and take a look at the marking guidelines, you're going to see in the marking guidelines that there are 4 other methods that you can use to calculate and come to exactly the same conclusion, that V2 is 3 volts. But I'm going to leave it here for now and allow you to try the other methods and to check those yourself. Question 8.6 begins with new information. They say a length of wire of negligible resistance is used to connect point P to point Q in the circuit. How will the reading on voltmeter V1 be affected? Choose from increases, decreases, or no effect. Explain the answer, and for this you're going to get 4 marks. You'll obtain 1 mark for writing down or choosing the correct conclusion, and 3 marks for your explanation. So we need to at least make 3 valid points in the explanation to obtain all 4 of our marks. So we start off by looking at the circuit on the left hand side. This is the original circuit, which I drew a little bit differently so that we can make better sense of it. What is V1? V1 is the voltmeter that is connected across the ends of the battery. This battery is connected to a closed circuit. So we know that V1 is measuring the external voltage. Alright, remember, whenever we have a circuit with a battery, there is voltage that is lost to the battery because the battery has internal resistance, and then the rest of it will be supplied to the external resistance or the load. So what we're now going to do is we're going to take point P and we're going to connect it to point Q. At first glance, it seems as though we are creating a short circuit, but this is not actually true. When we create this connection, we are actually making P and Q, in a sense, 1 point. And the reason I say so is because this conductor has negligible resistance, which means it has no resistance at all. As a result of this, resistor X, which is the 4 ohm resistor, is now connected in parallel to the 2,4 ohm resistor. We can redraw the circuit as is done on the right hand side. This is the new version of the circuit. So what have we done? We have taken a resistor that was in series and removed it. And then we took that same resistor that we removed from series and we added it in parallel. Now, when we take a resistor and remove it in series, it decreases the total resistance, or the effective resistance, or we could refer to the load. When we add a resistor in parallel, it decreases the external resistance or the load. So as a result of this connection of P to Q, we are decreasing the external resistance. That is what we're doing. So now we ask ourselves, if we decrease the external resistance, what is going to happen to the rest of the circuit? I would like to remind you, firstly, that if we are looking at a battery, the EMF of the battery is going to be a constant value. And in this section on electric circuits, we know that the internal resistance is going to remain constant as well. So we're going to keep these values in mind because the fact that they are constants is going to have an effect on what happens to V1. So if the external resistance decreases, we know that the total current in the circuit is going to increase. Resistance is the opposition to the flow of charge. So if resistance decreases, current increases. In grade 12, you learn a new formula that says that the EMF is equal to capital R, the load plus the internal resistance. If we expand, we get IR plus I small r, where we know that I capital R is V external, and the other value, I multiplied by small r, is V internal, the external voltage and the internal voltage. So let's start off by reminding ourselves that there are constants in this formula. The constants are the EMF and the internal resistance. They're going to stay constant. Now we have said that the current is going to increase. That is what's going to happen to that. If the current increases, then it means that V internal, this quantity, is going to increase as well. Since the EMF is constant, if the internal voltage increases, it means that the external voltage is going to decrease. The battery, if it is giving or losing more potential difference, or rather voltage, then it means it has less voltage to supply to the external load. So in the end, since V external is actually the reading that voltmeter 1 is measuring, we can come to the conclusion that the answer to this question is that the reading on V1 is going to decrease. So for writing the word down, decreases, you're going to get 1 mark. Now we need to state the points which I have just explained. Number 1, we say the total resistance decreases. That will get us 1 mark. Then we say the current increases. That is the next mark. And lastly, V internal, as mentioned over here, is going to increase, leading to V external, which is what V1 is measuring, decreasing. You obtain your marks for this statement, that one, this one, and this one over here. For this final statement, you're not going to get any marks, but that is in fact the conclusion that we mentioned right at the beginning, that the measurement on V1 decreases. Grade 12s, this brings us to the end of this video. In the next video, we're going to be looking at the section on electrodynamics, which deals with motors and generators. I hope to see you in the next video.